From the massive studios in Raleigh, North Carolina, this is the Cloudcast with Aaron Delp and Brian Gracely, presented by A Cloud Guru, bringing you the best of cloud computing from around the world.
Good morning, good evening, wherever you are, and welcome back to the Cloudcast. We're coming to you live from the massive studios here in Raleigh, North Carolina. We have myself, we have Brian, and then we have two Simons as well that we need to introduce. But first of all, Brian, how are you doing, man? It's been a while since we've been on the show together.
I'm good. It's good. Yeah, it's good to be doing a show together, and this is probably as good as any of show since it's not only friends of the show, but once again we get to dive into a new startup and a new technology space, and so this one's going to be fun.
So and also before we introduce, this is actually yet another milestone on the podcast. Two alumni from two previous companies now working together at the same company and back on the show. So we have returning alumni, but in a very unique scenario here. And so we'd like to welcome to the show, first of all, Simon Crosby. Simon, you were previously at Bromium when you were on the show, and then Simon Aspinall previously through Virtustream. And so if you don't mind, both of you take a second, introduce yourselves, kind of introduce the new role as well as the new company.
Sure. Well, thank you. It's a great pleasure to be back. This is Simon Crosby. My role, by the way, is CTO at SWIM.AI. And previously I was CTO at Zen Source. We did Zen, and then we did Bromium, which was using virtualization to do security. SWIM.AI is a dream come true. Plus, I get to work with Simon the Smarter, which is Simon Aspinall.
That's very kind of you, Simon. And this is Simon Aspinall speaking. I look after sales and marketing for SWIM. And as the guys mentioned, my previous life, I spent 5 years at Virtustream, helping to build an enterprise cloud business. And before that, a very long time at Cisco. So it's really good to be on the podcast again with you.
Guys, first off, as we mentioned before, great to have you back on the show. Congratulations on both of the previous things that you've been working on. Virtustream, great exit over $1 billion. Bromium doing really, really well and everything. But you guys decided to get into kind of a new space, right? You were in cloud, you were in security, and SWIM.AI is very much going to be in a different place. It's going to be in edge computing, and it's going to be in AI. What drew you to that space, and what's sort of, because I know both of you are unbelievably kind of passionate about what you work on. What's the driving force with this, both passion wise, but also market and technology fit?
Well, this is Simon Crosby. So I'm this for me this is an opportunity to go back to my roots as an academic computer scientist, an applied probabilist, which you should think of as a machine learning guy, and a computer scientist. And it's kind of, the timing of this is just perfect because I was watching this cloud world and we're seeing fabulous growth of cloud and the use of AI and ML. But I was watching people at the edge struggle with copious amounts of data, too much data to actually do anything on. And SWIM is essentially an answer to what I believe will become a crying need, which is the need to process data at the edge and to glean insights on the fly. Simon?
And from my side, after 5 years in the cloud world, I saw a lot of challenges coming up around some big data projects, a lot of challenges coming up around how you handle the enormous amount of data being generated at the edge. With a lot more smart devices and sensors and distributed computing out there, there's an awful lot being generated. And that's what I found really compelling about SWIM.AI, this whole idea that you combine edge computing techniques so that you're able to reuse what's already available, and then you apply machine learning and some advanced analytics all in the same space was really impressive. So that's what led me to join the company.
Excellent. Well, listen, let's dive into it a little bit. Let's sort of start with the basics, right? So we've been sort of similar to you guys. We've spent a lot of time talking about cloud on this show. The last 6-8 months, we've tried to dive into edge and AI a little bit more. We've had a couple of shows about that. The immediate thing that sort of we're starting to understand, we're trying to connect the dots is, obviously there's a ton of devices out there, a ton of different types of computing devices. There's a ton of data. and there's a ton of potential for value to be created, captured and created. Walk us through the basics of, that part of the industry, right? Like a lot of folks sort of understand the central part of cloud, but at the edge, what are some of the kind of core elements of, how we have to collect data, how we have to store data, what can you transport in a reasonable time with, edge networks versus core networks, and, walk us through some of the basics that as people are learning this stuff, they should be, kind of cognizant of.
Okay, this is Simon Crosby. I'll have a go with that. I think it's important to distinguish between cloud native app and the stuff that's out there today. So cloud native things like stuff that runs on your iPhone and so on, these are built to use different networks and so on. And often the technologies that are promoted and very successful there are ones which are already running in the cloud. So data is already going to show up someplace in the cloud. And if that's the case, why the hell would you put it in the enterprise? That's different than somebody who's running a city, somebody who's running a factory, anybody who's dealing with data that is already being delivered from SCADA, from oil and gas and so on. So we have trillions of dollars of assets out there which are spewing out vast amounts of data. And there's a great desire to be able to process this data and glean insights from it. The problem is, of course, moving this stuff, storing it and processing it. And there is an enormous challenge in a traditional enterprise related to the fact that really humans have not kept track here because of the growth of technology. There just is a great shortage of people with cloud skills, with the skills in big data, the skills in analytics and so on. IT is trying to get out of the business of being an IT, and they just don't have the people to deal with this stuff. So it's a tsunami of at least two proportions. One is that there's this vast amount of data. By the way, ARM shipped 5 billion in Q4 of last year. So there's an indication of lots of data for you. And so there's a huge amount of data, and there's a huge lack of skill set to store it, interpret it, and there's an inability to deal with the complexity of moving it over large networks and so on.
And one other element to add to that one, we're seeing a lot more devices appear at the edge. And now that the compute power you can put into them is ever increasing, the amount of information being produced is escalating very rapidly. Previously, what you used to have sitting at the edge would just be a basic sensor, and then you'd have a server somewhere trying to collect data out of that sensor. What's happening today is people are increasingly putting embedded chips, which are extremely cheap, into almost any device. And suddenly you're ending up with lots of data sources, all chattering away, generating data. And the challenge now becomes, how do you handle that data? How do you make decisions on it quickly? And how do you handle the mechanics of being at the edge? I guess even the edge is a bit of an amorphous concept, that you want to get as close as possible to where the data is being created. And the volumes of data now being thrown off by the edge devices is phenomenal. And when you try to backhaul that over a patchy local network, and then you have to pay to store large volumes of data centrally, that's a set of challenges which is defeating a lot of people at the moment.
So maybe we can make that real. The city of Palo Alto in California generates about 4 terabytes a day from 200 traffic lights, 200 intersections. Okay. And so everybody wants to be able to hop in an Uber and never see a red light, get there fast, and so on. Everybody wants their deliveries to show up quickly. Emergency services want to go through the right routes. But moving 4 terabytes a day, figuring out what to do, is just beyond the capabilities of most people.
Right. Yeah. I mean,
it becomes a signal versus noise aspect of, in one hand, it is an advantage. We're getting all this data. But on one hand, it's a disadvantage. We're getting all of this data because there is so much data being taken in and ingested. But how do you make sense of it? How do you make sense of it as quickly as possible so that you're not consuming in core, but you're consuming at edge or computing at edge, if that
Correct.
makes sense. Am I interpreting that?
Absolutely. And so let's go through what the industry receives message is today. First of all, there's an assumption that you will store all of this data and then train a machine learning model on it. And maybe you'll do that locally or or maybe you'll do it in the cloud. That's neither here nor there. That's really a choice, an architectural choice. And then you'll maybe figure out, what you should do better. That's batch style learning and response. And it's problematic because that isn't useful to Uber. Uber wants to know when the light's going to turn red or green. And so there is a need for real-time responses out of the edge in response to the environment as it changes around you. And so the idea of shipping vast volumes of data to somewhere, cloud or an enterprise data center, for batch-style learning and response is kind of out of line with many of the use cases.
So that sort of begs the question, how do you, the amount of data is not going to necessarily go down. How do you start to get a grasp on, how do I keep the data somewhat local, but, push these learning models, these, kind of, I don't know what the right word is for sort of the training models and all. How do you push those out to these devices that are, small ARM devices, right? They seem like small that's the piece that's always sort of confused me is, how do you put enough either storage capacity or computing power to make it capable at the edge?
Yeah. So, the amazing thing is that we worry about performance, but in fact, the architectures that we use today are the biggest stumbling block to great performance. So here's how it works in, say, something which is stateless or restful, even something like AWS Lambda or function. You have an event happens, some function gets triggered, you get something from a database, you compute on it, you store something in the database, and then you forget everything you just did. And the biggest barriers to performance there are these stupid lookups and saves to a database, which take you milliseconds. But I've got a CPU sitting on the edge, even if it's a relatively wimpy-looking ARM, which is running on the nanosecond timescale. So I've 10 to the 6 more clock cycles between your network packets to go to some remote database. And so it turns out there is a vast amount of spare compute cycles at the edge if you just have a stateful architecture instead of a stateless architecture. And so this notion of pushing statelessness, this restful architecture to the edge, is in perhaps the antithesis of good performance. Okay, so SWIM addresses this, first of all, by doing something which you could think of as being stateful Lambda or stateful functions right out at the edge. So SWIM processes every piece of data statefully. That is we're going to talk about the distributed actor framework, essentially. And if you're familiar with Orleans or Erlang, perhaps, then you'll know what I'm talking about. We're going to instantiate for everything in the world, every traffic light, every sensor in a cookie factory, an actor. And we sometimes use the term digital twin for that. And every one of these actors consumes the real world data from the real thing statefully. That is, it remembers between events what it just did, and it remembers it privately. So there's no database. We're not storing data. Each one of these actors is consuming data, processing it, and the state of the system is therefore the state of all of the actors. Okay? And SWIM as an edge computational fabric is an implementation of the distributed actor model. We use that to instantiate the digital twins that then consume data from their real-world siblings in real time. And it turns out that you can do amazing things, literally amazing things, on very little compute. So let me give you some examples. If I tried to solve the problem that I mentioned earlier of predicting what was going to happen to the traffic lights in, say, Palo Alto, in AWS using Lambda, that's a problem that comes out at about $5,000 or $6,000 a month. And so roughly $50 per intersection per month, which is just greater than economically viable. And if you do something like purchase an NVIDIA Jetson board, which is a $200 board, which is an ARM and a small GPU, you're done for all time. Okay? So the key point here is that the correct application of both computational architecture and the existing CPU and capacities at the edge can give us this astounding ability to learn. We'll talk about learning in a minute, at the edge and do some amazing things.
So just to add to Simon's commentary here, so the approach that SWIM takes is very different than everybody else's client-server style model. SWIM is a very lightweight piece of software, can be as small as 2 megabytes in size. You can drop that software onto an edge device, existing edge device, and then that software talks to other instances of SWIM on other edge devices. It then pulls all of that compute together to form a compute and a data processing fabric. So effectively taking advantage of all these stranded CPU elements sitting out at the edge. And then it's able to run data ingestion, data reduction, data analytics, and the machine learning models that Simon was just talking about entirely at the edge. And that gives you a number of great advantages. Obviously, you get to use all of the compute without having to wait for the latency of network. You're able to look at all of the data as it's being created, which means you don't have to pick and choose what you send back because you get full access to everything as you need it. And because you're dropping a model locally, that model very rapidly learns from the real-time data it's seeing, and it builds a mini model of what it's looking at, whether that's a sensor or a machine or a manufacturing line or a plant. And it learns based on the real data as it comes in, and it can train itself very quickly because it's getting to see what the results are a minute later or 5 minutes later. So
that's a really important point, Simon, that you just made, which is that the industry, the received message from the industry is you train your models based on training data in the cloud or somewhere, and then you maybe distribute a model to the edge. I'm going to be somewhat bold here and state this. There aren't enough humans on the planet to do this. Okay, there just aren't. And so what we have to do is we have to create systems which are self-training. They have to build their own models from the data. And so what SWIM does is effectively pick out the sensors or the intersections or whatever they're reporting in the data, and then repeatedly train. So every new set of data samples that comes in is thrown into a neural net at the edge, and we're running one neural net for each, and these are deep neural nets, one for each one of these twins, these digital twins, so one for each intersection, say, in the traffic scenario. And the job of that neural net is to predict the future. And so every new set of sensor readings goes into that. It predicts an output, and then we get an opportunity to match that with reality. And if it equals reality, then we're doing great. If it isn't, it's an error. But the error is then back propagated through the neural net, and the neural net gets better. And so these systems, even though they don't know what they're looking at, can build neural networks for the thing that they are training on. And after a while, they get really good. More than that, they can tell you how good they are because they estimate the difference, a distribution of their own error against reality. And so you just plug this thing in, and after a while, it's going to be predicting. It'll tell you when it's ready to predict with great accuracy, even though it doesn't know what it's looking at. So I'm going to be very clear here. Exactly the same software. If you plug it into something entirely different, we've done that. So, for example, tracking, backup battery recharge rates and voltages, we'll predict when batteries will fail 48 hours before they fail. And we do that nearly perfectly. And it's the same software that predicts nearly perfectly when every traffic light will change in the city of Palo Alto. Okay. So the key point here is that these models can self-train from the data. You end up with a model which is highly specific to the particular thing that you're watching. And what I mean by that is this: the intersection of Emerson and University in Palo Alto, that model is particular to that university and exactly how it behaves, and totally useless anywhere else on the planet.
So let me ask, go ahead, Aaron.
Sorry, I was just going to say, and the great advantage then is that the software throws the results up either to a user interface, so a graphical real-time interface, or to an API, so that the users of the system or the manufacturing plant or the environment can see exactly what's happening. They can have flags that show when something strange starts happening. It can identify correlations, and it can make forward predictions going forwards. And you can and obviously that data is the gems that you found out of the edge data, not the raw data, but actually the results. Or you can put the same thing up to an API and have it used by other applications or other use cases.
So another terminology question that we kind of came across here was, I just wasn't real clear on this one, is the concept of digital twins. What exactly does that mean, and what does it do? Because I felt like it was important, but I wasn't quite connecting the dots on it. So can you help with that one as well?
So historically, the concept of a digital twin was based on a design time asset. So I designed some complicated widget like a jet engine, and I have a rendering of it and so on, and I can use that in an operational context, say perhaps with a HoloLens or something, to understand better how the real thing might be behaving, because I have access through some augmented reality capability to impose both the design time view of the thing together with the real world view of the thing and try and figure out what's going wrong. Our view of a digital twin is actually quite different, and it's built from the data. That is, we start up with no notion of what the thing is that we're watching, and then we build a model, which, by the way, it's basically a program which behaves like the thing. So it's like this. Imagine I sat you down next to an intersection, and I said, don't leave this place until you understand exactly how it behaves. And I could ask you, given the traffic right now, what's it going to do next? Effectively, we're learning a program, which is a black box program, which is given some inputs, how will this thing behave? And so our notion of a digital twin is essentially the first one I've encountered where you build the digital twin from the
Okay. So
think of it almost just as a digital representation of a real world object. It's a model that can tell you how a traffic light's going to behave. It's a model that can tell you how a manufacturing machine will behave because it's learned on the data. It kind of literally making a digital twin of a real world object.
It doesn't know how it works, though. So, at least in our case, it doesn't know how it works. We learn based on the black box observation of its interaction with the world.
Okay, so a couple of basic questions because I'm thinking through this here. So the SWIM software. So SWIM is the name of the company, but SWIM EDX is the platform and the software. That software you can put onto these remote devices. So my thinking is, like if I have a camera, for example, or some sort of sensor inside of we'll stick with the intersection example, like are those platforms like open enough that you can put your software on top of them, or are these things, so if I'm an existing city, is that that's possible?
Well, so in general, what you hit on is that in this market, it's not a traditional enterprise IT replacement market. It's not like somebody buying a new hard disk or a new version of a database, right? So the routes to market there traditionally have been through equipment vendors. So folks like the Rockwells and Honeywells and Ingersoll Rands and Hitachis and so on, who try and make better widgets and who are interested in making their equipment, but also their customers' entire factories or industrial deployment better. And so we work with that category of partner. There are also folks who have spare compute lying about near to their assets. So we've been involved in a project where we're providing insights and accelerating the assembly of aircraft, which is quite fun. This is an RFID use case. Ultimately, we ended up running very close to the network that is on the factory floor, but on spare x86 cycles in the data center. Okay. So the key thing here is that edge varies. The notion of edge varies between use cases and customers. And the key point is that SWIM is deployed as close as possible to where the data is, and it can smear literally between a tiny little embedded device and the cloud. And when I say smear, I mean this is all part of one fabric. So SWIM builds a peer-to-peer fabric in which it understands the capacities of each one of the nodes that it's running on, and it will move compute automatically to the right place given where the data is and what resources are available to do the work. Okay, so it's not machine learning on a tiny little embedded microprocessor, but if there is a something with a few gigs of RAM, right, or a few hundred megs of RAM nearby, then the compute will move to that, and it will just do so seamlessly.
Okay, and the concept, like you said, we have big sort of global ambitions or local ambitions, and being able to apply the right number of data scientists to that is going to always be sort of a failed problem. At what point, though, does the system sort of figures out what an environment looks like? At what point does somebody who is a traffic expert or a machine expert, like when do you ever connect those two things together?
No.
Somebody who's got domain expertise with your system that observes things.
John, that's the perfect question. So, and there are a bunch of really cool use cases. So I'll give you one, which is kind of fun. We are already deployed. Within a year, we should be running with our partner Trafficware, a service which predicts the future state of about 60,000 intersections in major U.S. cities. The goal is to get to 300 or so thousand of them as quickly as possible. So here what we do is we simply observe what's happening given city data. And that's voluminous, ugly, horrible voltages from sensors and things like that. It turns into very low-rate predictions delivered via Streaming API, which is presented out of Microsoft Azure. And that API simply allows a third party like Uber or UPS or whatever to run their routing algorithms and hit that API to find out what's going to happen. Okay, so there's an example of what you just said, which is, well, what does the data mean? Who's going to make sense of it? In this case, actually, Uber is. They're going to figure out that in 2 minutes' time, a particular light is going to go red, so they want to turn right. Okay, so that's one use case. The other one is that, we could be learning where assets are in 3 space, say in a manufacturing environment. And then instead of tracking RFID tags, we're tracking, say, the undercarriage of an aircraft. That's of interest to the SAP ERP system in the enterprise, even though we have no real value. We don't know what that is, right? Mm-hmm. But the SAP system is wanting to track wheel or what are sub-assemblies of an aircraft. And so inevitably what you end up with is this, or at least maybe a summary of what SWIM does is we build these digital representations, which are essentially augmented reality versions of real world things, which can tell you in a statistical sense about their past. They can absolutely tell you about their present, and they can project the future. And then it's up to you to make use of it in your particular way. Now, each one of these digital twins presents, it drives both real-time graphical objects. So, for example, pie charts and distributions and so on, which can be just readily composed into a browser-based UI. But it also presents a real-time streaming API. And so if you're interested in understanding how some assets are working or what they think about the world, you simply subscribe to their streaming updates, and they will give you a low-rate stream of high semantic value, so semantically enriched data, which tells you stuff that is useful to your particular use of those twins.
No, that makes sense, and that was sort of my third follow-up question, which is going to be, where at what point does an ecosystem kind of fit into this and other tools wrap around it? But I think you explained that really well. Well, listen, guys, we love these conversations because it's you're always working on stuff that's very much coming down the road because of your background. You've got the ability and the team to kind of go after these big challenges. If somebody, beyond just going to the website, like what are good ways for people to get engaged with you guys if they think that they have an edge challenge that SWIM might be a good fit for, or at least, a conversation to have with you?
So we'd love to hear from anyone who has edge data problems. I'd recommend take a look at SWIM.AI. We've got some examples up there of running systems where we've created applications or user interfaces for people, lots of different sectors. And yeah, we would love to have a conversation with anyone who has these type of challenges. We think of SWIM as a small piece of software you can add to either existing hardware or existing software to add edge intelligence to what's happening. So In a lot of cases, as Simon mentioned, we work with the suppliers to various sectors. So folks who make devices or provide devices, machines, traffic systems. And in a number of cases, we're being used to help simplify edge data problems, either reduce the volumes, improve the quality, or just make the whole process more efficient by saving costs and storage and throughput. So any of those kind of challenges, we'd love to hear from folks.
Well, listen, I think, guys, with that, I think we're going to wrap it up. Like I said, we could dive into this for a lot longer, but just for the sake of the show, we're going to wrap it up. Great to have you both on. Best of luck, and hopefully we'll get a chance to have you back on again soon, 6 months, 8 months, and kind of tell us where things are going. But folks, for that, we're going to wrap it up. For myself and Aaron and both of the Simons, we're going to wrap it up. Thank you for listening, as always, and we'll talk to you next week.
Thank you for listening to the Cloudcast. Please visit thecloudcast.net to find more podcasts, show notes, and everything social media. And visit acloud.guru for all your cloud training needs.